So, in our search so far for finding some analog to Gauss's law, we did discover something very interesting. We did discover a direct analog, but it's not something we can really sink our teeth into in order to calculate anything. We just get zero. So we have to go back to the drawing board a little bit. Let's go up and take a look at what we had tried. It was a very good start, right? What we said was, well, the electric field case gives us a very interesting formula in the form of the divergence of the electric field giving us the Gauss's law. So we said, well, analogously for the magnetic field, let's try to take its divergence. But magnetic fields are just a little bit different from electric fields. They're not exactly the same. There's one thing that always comes up in the magnetic field case that we've seen over and over again that you don't see in the electric field case. And we see a good example of it here. It appears in almost all of our formulas, as I've said, have this kind of cross product form in them. So, in our search then for some kind of analog to Gauss's law, maybe instead of trying the divergence, we should try a different type of derivative. We learned something from this derivative, but maybe the better type of derivative would be the one that naturally involves this cross product, because that is what always shows up in magnetic field theory. So let's try that then. So let's give this another try. So we're going to try again, but this time what we're going to do in looking for some new physical law that will be useful, let's look at a derivative that has a cross product form in it, namely the curl. Let's calculate the curl of the magnetic field with respect to its arguments and see then what we might get there. Now, we'll carry out this computation. So this then is going to give us the curl, and I have to copy again my formula for the magnetic field, and I'm going to write it again in the form that links to the electric field, because we know a lot about the electric field. So there were our fundamental constants, you will recall, the sum over all of my particles, each of their velocities, and then that velocity is cross product with the electric field that is created by that particular point charge. So that is the form that we have to contend with. Once again, we can factor out the constants, because this is just a derivative of a constant times something. Always gives me the constant times the derivative of the something. And then I will have the derivative, in this case the curl, of a sum of terms. But the derivative of a sum is always equal to the sum of the derivatives of the corresponding terms. So again, I'm taking derivatives with respect to r. I just don't want to forget that. So then when the derivative comes inside the sum, I've got the curl now of a cross product of the velocity of each particle, cross product then with the electric field coming from each of those individual particles. Well, looks like it's time once again for another vector identity. And this is actually a fairly complicated vector identity, but it simplifies. It's got 4 terms in it, because I've got derivatives of 2 different things, and I've got cross product of cross product. But because v is constant, as we saw last time, that makes things a lot simpler. And since v is constant, there's a simpler vector identity that comes into play here. And that vector identity gives me then the following result, that this combination of derivatives and cross products ends up giving me just the velocity of the ith particle times the divergence of the electric field associated with the ith particle. Well, now that's something interesting. We know something about that divergence. Minus then, and remember we have to get vectors out of this, we get the velocity of the ith particle dotted with the derivative then of the electric field associated with the ith particle. Okay, well, as before, we have to analyze our 2 terms to try to understand what they are telling us. This term we certainly recognize. That is Gauss's law for the electric field. We know that what this represents is the charge density associated with the ith particle and then, of course, divided by epsilon naught. So let's now write what we have, because we seem to be making some good progress here. So what we've learned then is that when we take the curl of the magnetic field here, right, what we seem to be finding is we get two terms. The first term has this rho I divided by epsilon naught, but there's a prefactor of epsilon naught out front, which is going to cancel out nicely for us. So that first term is going to give us mu naught epsilon naught sum over all of these particles. And then what's going inside the sum has the charge density associated with each particle, rho I, times vi, the velocity of that particle, divided by epsilon naught, just copying the formula. But what I was just noticing is that these two epsilon naughts are going to cancel out. Well, that looks very nice, because now I have something that has mu naught in it. This is very promising. This is something I would expect for a magnetic field case. And then there's this additional term that we have to deal with, this second term that's going to come in. I'll write it with a plus sign. You've got mu naught epsilon naught, but remember, mu naught epsilon naught is something that we also know something about. We'll come back to that in a moment. Then we have sum over the particles. What's left over is there's this minus vi. I don't want to forget my minus sign. Dotted the gradient of the electric field associated with particle I at location R, like so. Now, this term is very interesting because we know what mu naught epsilon naught is. We've seen that before in our relativistic considerations. We'll come back to it some more later, but we happen to know secretly this thing is equal to 1 over c squared. This is something that in general is going to be quite small. It's something that oftentimes, but not always, we can ignore. So the fact that this is usually it's small, right? It's usually a small term. That means generally we can ignore it. And so I want to focus on what this term is telling me. Well, this term, I want you to notice, is that if I were to rewrite this just slightly, I get something very interesting and intriguing out of this. Rho I, right? That, it looks like something very similar that we've seen before. If I look at the charge density associated with a particle times the velocity of that particle, you will recall that we've seen this combination before. This corresponds to, we sometimes would write it this way, the density of those particles times the charge of those particles times the velocity of those particles. Those are all the types of combinations that we've seen before. Those all correspond precisely to what we saw in our study of the flow of current. That just represents the current density associated with the ith particle. So this sum then, what it is giving us, what we are learning here is that the curl of the magnetic field equals this one constant mu naught times the sum over all the particles that might be moving through a given region of their corresponding current densities. So when I add those all up, I just get the total current density flowing at location R. And the remaining term is then something that's quite small, and usually we can ignore it. And when we ignore it and take just these two particular terms, this is what is known as Ampere's law. And that is a very powerful law that we can use to calculate magnetic fields. And we will look at this more in our following discussions.